Welcome to The Explainer. Today, we're jumping into a huge idea in calculus, one that's kind of summed up by that old saying, it's about the journey, not the destination. We are talking about the limit of a function.
Okay, let's just dive right in. Take a look at this graph. At first glance, it looks like a totally normal, simple straight line. But there's a catch. See that tiny little hole right at x equals 2? That open circle, that's our puzzle. It's telling us that the function isn't actually defined at that one exact spot. So you can't actually stand on the point where x equals 2, right? It's a hole. But just imagine for a second you're walking along that line, maybe from the left or maybe from the right. As you get closer and closer and closer to that hole, where does it feel like you're going? The path is clearly heading towards a very predictable value, even if it never technically gets there.
And that question, that's really the whole idea behind a limit. See, we're not asking where the function is at a specific point. We're asking, where is it going? What value is it trying to reach as we get infinitely, microscopically close to that point?
Exactly. The limit is all about how the function behaves in the neighborhood of a point. It's the trend. You can almost call it the intention of the curve. And that's totally separate from whatever might be happening or not happening at that one single isolated destination.
And this slide right here is just a perfect illustration of that difference. Look really closely. At x equals -1, the function's actual value is 4. That's what the solid blue dot tells us. But if you trace the curve with your finger from either side, where are you headed? You're clearly approaching a height of 3. So the limit is 3, even though the function's actual value is 4. They can absolutely be different.
So how do we find this value it's getting so close to? Well, aside from just eyeballing the graph, we can get way more precise by zooming in on the numbers themselves.
Now, what's really cool here is seeing two different tools tell us the exact same story. On the left, you've got a table of numbers. Just watch what happens as the x values sneak closer and closer to 0, from the negative side and from the positive side. The function's output is just homing in on the number 1. And now look at the graph on the right. It visually confirms the exact same thing. The curve is zeroing in on a height of 1 as x approaches 0.
And this is the idea of formalized. All it's saying is this: the limit of a function as x approaches some number a is another number L if we can get the function's value as close to L as we could possibly want just by picking an x that's close enough to a.
But, it's not always so simple. It's not always this one nice, clean path. So what happens if the function doesn't approach the same value from both sides? What if the path splits? Well, to handle that exact problem, we have a great tool called one-sided limits. The idea is actually pretty simple. Instead of looking at the approach from both directions at once, we just analyze each side separately. We find the limit from the left, using values just a little smaller than our target, and the limit from the right, using values just a little bigger. And here we have a perfect example of one of these splits. It's called a jump discontinuity. If you trace the graph as x gets closer to 2 from the left side, your finger ends up at a height of 3. But if you come in it from the right side, you end up way down at a height of 0.
So here's the crucial takeaway. If those two one-sided journeys don't lead to the exact same destination, then we have to say that there is no single overall limit. At that point, the limit simply does not exist, and you'll often see that shortened to just D and E.
This is the golden rule you have to burn into your brain. For a general two-sided limit to exist at a point, two things must be true. 1, both the left-hand and right-hand limits have to exist. And 2, they have to be equal to each other. Simple as that.
Okay, so we've talked about functions that approach a nice, clean, finite number. But what if they don't? What if, as we get closer to a certain point, the function just, shoots off the charts, growing or shrinking forever?
This is what we call an infinite limit. And what it does is create this really interesting feature on a graph called a vertical asymptote. That's that dashed line you see. Think of it like an invisible electric fence that the function gets infinitely close to, but it can never, ever actually touch or cross it. So really, it boils down to this. If you find that your function's values are heading toward either positive or negative infinity as you get closer and closer to a certain x value, boom, you have officially found a vertical asymptote at that x value. All right, time to put it all together. Let's take everything we've just talked about, one-sided limits, two-sided limits, infinite limits, and see if we can figure out what's going on with this more complicated graph at a few key spots.
Let's break this down.
First up, at x equals -2. That's our classic hole in the graph. The path from the left and the path from the right both lead to a height of 3, so the limit is 3. Easy enough. Next, at x equals 1, we've got a jump. Coming in from the left, you're heading for 6, but from the right, you're only heading for 3. They don't match, so the overall limit does not exist. And finally, look at x equals 3. From both sides, the function just plummets down toward -infinity. That's our vertical asymptote right there.
So we've gotten pretty good at figuring out what happens when x closes in on a specific number. But that kind of opens up an even bigger, maybe crazier question. What happens when x doesn't close in on anything? What happens when x itself just heads off toward infinity? Well, that's a journey for our next explainer.